Hello all. In today's session we will talk about the next hyperparameter called as regularization methods. We will discuss few regularization methods to avoid overfitting. So far we have done with all these hyperparameters, and in today's session we will cover this regularization techniques to avoid overfitting, and these are the hyperparameters that we will be discussing, which define different regularization techniques to avoid overfitting. So these will be the techniques that we will be discussing here: L1 and L2 regularization, dropout layers, data augmentation, and batch normalization. These are the four regularization techniques which are used by machine learning models to avoid overfitting. We have talked about overfitting in the previous sessions. There are two different ways to solve the overfitting problem. The first is adding more amount of data. That is, you add more rows in the data set. And the second method to add more data is data augmentation, where one image is flipped in different directions, flipped vertically, horizontally, and different methods are performed on that particular image so that number of images are generated with one image only, thereby increasing the amount of data. So this is the first method to avoid overfitting. The second method is reducing the complexity of the model. If the model is more complex, then it will try to learn all the features which are provided in the training data. That is, it will not learn the data, but it will by heart all the features which are provided. Thereby it performs very well on the training data due to this complexity of the model. So we can reduce the complexity of the model by implementing any of these methods. Dropout, that is dropping the neurons within the hidden layers, thereby reducing the complexity. The second method which will reduce the complexity of the model is early stopping, where whenever you find the testing error is getting increased, the moment you stop training the model. Anyways, these two we have already discussed. In today's session, we will talk about the regularization technique, which is used to reduce the complexity of the model, and reducing the complexity of the model thereby reduces the overfitting. So these are the regularization techniques that we will be discussing, L1 and L2 regularization. Now before moving on to the regularization techniques, let us have a quick recap of what overfitting is. Consider that this is the training data and this is testing data, and when I train the model for a certain time, the decision boundary which I get is in this way, which will very well it will fit with the data set. That is, it will capture almost all the data points. Now if I try to make prediction on the test data, it will not perform well. That is, it is not covering all the data points. That means the accuracy in the training data is more, whereas the accuracy in the testing data is very less. This is what called as overfitting. Consider a highly complex neural network. When the neural network is highly complex, obviously it will generate a highly complex nonlinear curve. To increase the linearity of the curve, what will I do is we will nullify few neurons within the hidden layer, and when I nullify the neurons, thereby decreasing the complexity of the model, instead of a non-linear complex curve, I will get a simple curve here, which is called as the decision boundary. Though it is not perfect, but it is not it is not non-linear also. It is a linear decision boundary which will be formed, which increases the linearity of the model. Now, overfitting can be understood by taking the regression problem. Consider the equation here, y is equal to mx plus c. So if I have n number of variables, I'll get a curve like this, and this curve is called as the overfitting curve, which will try to fit all the data points. So x1, x2, x3, all these are the data points, and the decision boundary what I have drawn is trying to cover all the data points here. And in the next case, what will I do is, I have only one feature and two parameters. So a straight line here will be enough, and this straight line is called as the best fit line, and this is the linear line. This increases the linearity. Now you need to have a trade-off between this first and the third curve. That trade-off can be considered by taking into consideration this curve. A curve between both these is a proper curve which is possible by eliminating certain parameters here, that is nullifying certain parameters so that we can have better smoother curve. And this technique to nullify the effect of certain parameters during the training process or nullifying the effect of neurons is called as regularization. That is the reason why we go for regularization, to increase the linearity in the model. Now in regularization, we will talk about this equation called as cost function, whose formula is 1 by n sigma I is equal to 1 to n yi minus y hat whole square, that is true minus predicted value whole square. The main aim of any of these machine learning models is to reduce this cost function. Now I will add a penalty term to this cost function. This penalty term will create a nullifying effect, because we are talking about nullifying few parameters to increase the linearity. This penalty term will create nullifying effect of certain parameters. And as the cost function is reducing, I have these two equations. I am adding, this is the cost function, I am adding this as a penalty term here, and for this cost function I am adding square. This is the penalty term. This is called as L1 regularization, and this is called as L2 regularization. And the difference what you notice here is you have weight and you have square of that weight. For example, if you have 10 data points, then W1 square plus W2 square so on till W10 square weights will be added up and multiplied by a term called as lambda by 2m. This lambda is called as, I can say it as a regularization factor or a hyperparameter, which will finely tune the proportion of linearity and non-linearity of the model. Now, whenever, if lambda value is high, then it will force to reduce the value of W. And if W is reduced and approximately equal to 0, then it will increase the linearity. Similarly, if lambda value is very less, then it will forcefully increase the value of weight, thereby increasing the non-linearity. Hence, this parameter lambda is called as the regularization parameter. So, these are the two equations which you need to remember, which are used for regularization to reduce the cost function or to increase the linearity as well as increase the training time of the model. And when you have Wj, it is L1 regularization. When you have Wj square, it is L2 regularization. L1 and L2 regularization are methods which are used to mitigate overfitting in ML models. These techniques are often applied when a model's dataset has a large number of features and a less complex model is needed. That is, to reduce the complexity, we make use of these two regularization techniques. A regression model that uses L1 regularization technique is called as lasso regression, and a model that uses L2 is called as rich regression. So L1 and L2 regularizations are also called as lasso and rich regularization techniques, and most of the regression models only make use of these regularization techniques. Coming to the first one, L1 regularization, also called as lasso, and lasso means least absolute shrinkage and selection operator regression. It will add the absolute value of the magnitude of the coefficient as a penalty term to the loss function or cost function L. Lasso regression also helps us to achieve feature selection. If n number of features are given and we would like to select only the features which are more important, in such cases we make use of this lasso regression, which will add penalty to that cost function, and this is the equation here. Similarly, L2 regularization is also called as ridge regularization method or ridge regression. It adds the squared magnitude. Remember that lasso regression adds the absolute value, and ridge regression will add the squared magnitude. So in most of the material, you can have simply lambda term also, and most of the time it is given as lambda by 2m also. Generally, let us consider this equation where lambda by 2m, where m represents the number of rows. Generally, an optimizer will calculate the derivative of the error function and multiply it by a learning rate, and then subtracts this from the old weight. Here, this is the equation for the backpropagation algorithm, where old weight minus alpha times of derivative of error with respect to that weight. Same is the case in the cost function, what we have used here for L1 and L2 regularization. L2 regularization does not make the weights equal to 0. It just makes them smaller to reduce their effect. A large regularization parameter lambda will lead to negligible weights. When the weights are negligible, the model will not learn much from these units. This will make the network simpler and thus reduce overfitting. Why? Because as we are multiplying lambda by 2m with w square, as this regularization parameter lambda is very high, then obviously it reduces the weight value, and when the weight value is negligibly small, then the model will not learn much from these units and it will make the model very simpler. So as the weights are getting reduced here, these neurons are getting nullified. This is how in Keras L2 regularization is done, where I have kernel regularizer as regularizers dot L2 of lambda. We need to import it from the Keras and then use this command for implementing L2 regularization. These are the differences. In L1 we add the absolute value, in L2 we add the squared magnitude, and the key difference between these L1 and L2 is L1, that is lasso, shrinks the less important features coefficients to 0, thus removing some feature altogether. So this works well for feature selection in case we have a huge number of features. Coming to the second method of reducing the complexity, dropout layers. Here what do we do is few percentage of neurons will be dropped from the input layer as well as from the hidden layers, thereby reducing the complexity of the model and increasing the training time also. Coming to the next method, data augmentation. This is the other method to avoid overfitting. You can see here, this is the original image and these are the augmented images of this original image. Various image augmentation techniques are here. Flipping, rotating, all these are the augmentation techniques that are implemented here, thereby increasing the number of increasing the data here. In data augmentation, this is how it looks in the Keras, where we'll import the image data generator, which will implement data augmentation. Coming to the next method called as batch normalization. Generally, we have these two methods called as normalizing and standardizing. Both have the same objective, that is, it will transform the data on the same scale. In normalization, we will get them to a scale of between 0 and 1, whereas in standardization, we will subtract that value from mean and divide it by standard deviation. In both the methods, mean will be 0 and standard deviation will be 1. These are the other regularization techniques which are generally used before giving that data as input. One of the pre-processing step we can say, once the data is normalized, that normalized data is given as input to my machine. That is, before the training, the data is normalized or standardized. Both has the same objective. When you have non-normalized data, then the training spree will be reduced. Now consider as a neural network training where the weights are getting updated, and what we consider here is stochastic gradient descent where the weights get updated. Now, what if during training one of the weight is drastically larger than the other weights? Then this larger weight will cause the output from its corresponding neuron to be extremely large, and this will create imbalance which will continue to cascade and then thereby increasing all the values wherever this output of this neuron is high. That means this high output from this neuron is given as input to the other neurons. That is, the output of one neuron is creating imbalance, which will continue to cascade through the neural network, thereby causing the instability. In such cases, batch normalization will be introduced. So what will batch normalization do? First step, it will normalize the output from the activation wherever it finds extremely large output of the neuron. How will it normalize? Subtract that value from mean and divide it by standard deviation. Second step in batch normalization is multiply that normalized output with an arbitrary parameter called as G. And the third step is add a second arbitrary parameter B to the second step. So we are talking about two arbitrary parameters here, G and B. These two arbitrary parameters sets a new standard deviation and mean for the entire data. Mean, standard deviation, G and B. These four are trainable parameters, that is, they can be optimized during the training process. As normalized is included, all the points get normalized, thereby increasing the speed. Now, why do we call it as batch normalization? Normalization we have already talked. Normalization is done before providing input to the neural network. So, one of the pre-processing step, once the data is normalized, that normalized data is given as input. And within the hidden layers, wherever you find extremely large output coming from the neuron due to large weight values, we go for batch normalization, which will normalize all the outputs of the neurons in the activation function. So what difference do you notice here is normalization is done prior to providing input to the model, whereas batch normalization is performed within the hidden layers of the network. So this will increase the stability also. As the normalization is done in the batches, it is called as batch normalization. You can see here, these are the inputs and I am performing batch normalization through at the hidden layers once the activation function is applied. Now how does batch normalization work? It will zero center the inputs, normalize the zero center inputs, scale and shift the results. These three steps what we have discussed in the previous slide. And this is the mathematical equations of batch normalization. This is mini batch mean and this is for variance. And subtract that mean and variance from the input so as to normalize the data. This is how batch normalization looks in Keras. From Keras we will import batch normalization, and these are the different functions that are imported from Keras. So this command is important, which will perform normalization when we import batch normalization from the Keras library. This is the end. Thank you all.